So welcome back to another video, and in today's video what we're going to do is a multi-unit system with a reaction. So we'll work through this I've got a practice problem. We're going to work through the entire practice problem, and I'll just give you some steps and tricks on how I would approach solving a problem like this. And like I've done in some of my previous videos, what we're going to do is we're going to read through the problem first, and we're going to identify any important information that we should probably record so that we can use it later on as we approach solving this problem. So let's get into it. A methanol production plant is reacting carbon dioxide with hydrogen to produce methanol and water. There's a feed stream entering a mixing chamber containing carbon dioxide, hydrogen, and nitrogen with a mole fraction of 0.005 nitrogen. So right away, we've got a good piece of information. We know the nitrogen mole fraction in stream 1. So Y1, let's write that a little better. Y1 and 2 equals 0.005. Okay. The stream exiting the mixing chamber that enters the reactor has CO2, N2, and H2 with a mole fraction of 0.28 for CO2, 0.7 for H2, and 0.02 for N2. All right, so we got a lot of good information in addition to that. So we've got, and we're going to assume that the stream entering into the reactor is stream 2. So Y2 CO2 equals 0.28. Y2 H2 equals 0.7. And Y2 N2 equals 0.02. Now, as a quick heads up for when we do our degree of freedom analysis, just remember that even though you have 3 mole fractions for stream 2, since there are only 3 components in stream 2, only 2 of them count as knowns. All right, moving on. The single pass conversion of H2 is 60%. Awesome. So single pass conversion, we can consider that like a fractional conversion because they're doing the same thing. Single pass speaks in terms of just the reactor, and a fractional conversion is always with respect to our reactor. So we can write that as F conversion H2 equal to 0.60. All right. The product stream exiting the reactor enters a condenser where all the methanol and water exit in a bottom stream. All right. So that's just important information for when you draw your process flow diagram. The molar flow rate of methanol in the bottom stream is 155 kilomoles per hour. Okay, so 155 kilomoles per hour. All right, and I have a block flow diagram that you'll get to see in a little bit. So I'm just going to write this out in terms of its variables. So N4 CH3OH equals 155 kilomoles per hour. Okay. Everything else exits in the distillate stream and is sent to a splitter that has 2 exiting streams. One of the streams exiting the splitter is a recycle stream that is combined with the feed stream in the mixer. Okay. And with this problem statement, what they're wanting you to look for is solve for all the unknown flow rates. Solve for all unknown n dots and get compositions as well. And get compositions. Okay. And as you see with this problem statement, you do have your reaction and it is balanced. So we've got CO2 reacting with 3 hydrogens, yields methanol plus water. Okay. And as we scroll further down, you see that we've got our block flow diagram and it's got all our information right there for us. Okay. And most of the time, I'm just going to point out over here by the condenser, most of the time when you have a bottom stream, it actually would be coming out the bottom and your distillate would come out the top. However, in terms of just drawing this block flow diagram, it was a little bit easier and cleaner to have my distillate stream come this way so that the splitter section going back to the mixer easily goes over towards the mixer. Just a quick aside, but the diagram is perfectly representative of what's going on. And now most of the time I know you would assume if the professor's asking you to solve that it is solvable. But as a double check, we're going to do a quick degree of freedom analysis just to make sure it is truly solvable. So we've got degree of freedom analysis. And as we do this, we're going to look for our ISVs. And in this case, we're looking for how many components we have in each of our streams. So in this case, stream 1, we've got 3 components. Stream 2, 3 components. Stream 5, 5. Stream 3, 5 components. Stream 4, 2. Stream 5, 3. Stream 6, 3. Stream 7, 3. So if we count that up, that's 3, 6, 11. I'm sorry, you can't even see this on the screen. There we go. Okay, 11, 13, 16, 19, 22. So we've got for our ISVs 22. All right, next thing we'll do is we'll look at our knowns. And in this case, we'll count up. So we got 1 for nitrogen, 2, 3. Now remember, because stream 2 has 3 components, only 2 mole fractions can count towards reducing my degrees of freedom. So that third one of Y2N2 does not reduce my degrees of freedom, doesn't count as a known. And the final one we've got is the molar flow rate of methanol in stream 4. So that gives me 4 knowns. So I'm going to write -4 because it's reducing my degrees of freedom. And if we're just keeping track of our degrees of freedom over time, it's 18. The next thing we're going to do is we're going to look at our independent material balances. And as a reminder for your independent material balances, it's going to be the sum of the material balances you can do for each of your units. So in this case, for the mixer, since there's 3 components entering and exiting, you're going to have 3 independent material balances. In your reactor, because although you start with 3 components coming in, you have 5 components coming out because we are making new compounds. And in that case, you can do 5 material balances. The next one, looking at the condenser, you've got 5 components coming in, so we can do 5 independent material balances. And then over the splitter, we're going to be able to do 3 independent material balances. And that now gives me, if we're counting up the independent material balances, we've got 3 plus 5 plus 5 plus 3, giving me 16 independent material balances. So -16, giving me 2 degrees of freedom at the moment. And now as we continue along, we'll look for other ways to reduce my degrees of freedom. And in this case, we do have a process spec, which is my conversion factor. So we have -1, right? Because we have a single pass conversion for hydrogen. So that will reduce my degrees of freedom by 1. And that's going to give me, right now, 1 degree of freedom. However, speaking of that reaction, anytime you have a reaction in your system, that's going to increase my degrees of freedom. So I'm going to have a +1, giving me now 2 degrees of freedom. And normally, that would probably be about where we're at in terms of the different ways we can reduce my degrees of freedom. However, we have a special unit in today's problem, which is a splitter. And with the splitter, what you can do is, or rather what you have to do for your degree of freedom analysis is incorporate splitter restrictions. And what I mean by splitter restrictions is that because you have a splitter and the composition of your stream doesn't change for any stream going in or out of the splitter, that actually helps you out and reduces your degrees of freedom. And the way we would calculate that, so splitter restriction is going to equal S-1 times N-1. So S for splits. So in this case, we have 2 splits because we have 2 streams exiting my splitter. And N is for the number of components. So for us, we've got 3 components, -1. And if we do the math out, what we'll get is we've got a splitter restriction of 2. And so that's going to be reducing my degrees of freedom by 2. So in this case, we got -2. And that is going to get me to 0 degrees of freedom. So I can solve this. Neato. Now, since the question just gave you a blank check in terms of what components to solve for, what we're going to do is try to identify which of my 4 different units might be the most convenient one to start on. So in this case, you know you've got one piece of information going into your, or you got one piece in stream 1, you've got 2 good pieces of information in stream 2. For the reactor, you also have your single pass conversion. That's another good piece. And then over here on your condenser, you've got a flow rate, the molar flow rate of methanol. And so now looking at it, it's most likely that you're going to be doing stuff over your mixer, or you have the most information over your mixer as well as your reactor. Now, most of the time, if you've got similar amounts of information between two different units, what you probably want to do is take care of the reactor. So we'll think about it as tie goes to the reactor. Just because there's a lot more things going on, you've got the molar flow rates going in do not necessarily equal molar flow rates coming out. So it's going to be a little bit more helpful to take care of the reactor, take care of all those different conversions or generation and consumption terms before you move on to the other units. And so that's why I would recommend go to the reactor. And now looking at it, to really start on the reactor, what we need is an N dot. We need an N dot for my reactor. But the only thing is I have an N4 dot for methanol. And let me scroll back up so you can see what I'm doing. So I've got an N dot for my reactor, or I'd like to have an N dot for my reactor so I can get moving forward and I can actually utilize all the other information I have. But the only issue is I've got an N dot for my methanol. So I really would like an N dot here, but I have an N dot for my methanol. And this is where we get to do something different. We can assume a basis. Assume a basis. And what that means with assuming a basis is that we're going to assume N2 dot of 100, and I'm going to say kilomoles per hour. The reason why is because my methanol flow rate is in kilomoles. So in terms of units, it just makes it a little bit more convenient for us down the line. So we assume a basis for N2 dot. So N2 dot, we're going to assume. However, if we're assuming a basis for N2 dot, what that means is I have to sacrifice another known flow rate. So we are going to sacrifice N4 dot. Sacrifice. It doesn't mean we're never going to use it. It just means for now, we're not. So no longer using, so we can't use N4 methanol. Can't use N4 CH3OH. However, once we solve for everything in the entire system, so once we solve for everything in here, we're going to do a scale up, where we're going to then scale up to get the correct molar flow rate for methanol and the true molar flow rates for everything else. But for now, we won't worry about that. Let's just start on our reactor and use what we know. N2 dot is 100 kilomoles per hour for now. So over here, what we're going to do is we're going to just redraw my unit. And I'm just going to focus on my reactor because, as you know, what we get to do within our system is we can draw envelopes around each unit. We can draw envelopes around each unit so that we just focus on one thing at a time. So for us, we're just going to focus on stream 2. We got a reaction and stream 3. And you know that you have CO2, H2, and N2 entering. And for Stream 3, you have CO2, H2, N2 exiting, but you now also have methanol and water. And then stream 2, you already knew that you've got Y2 of CO2 equal to 0.28, Y2 H2 equal to 0.70, and Y2 N2 equals 0.02. But not only do you know that now, you know N2 dot equals 100 kilomoles per hour. And now that you know that, you actually get all the flow rates because you know all the mole compositions. And the other piece we know is F conversion of H2 equals 0.60. So now that we've got everything set up, what we're going to do is an extent of reaction table. So with the extent of reaction table, what we're going to do is we're going to look at what we start off with and what do we end up with. Now, I'm just going to make a note that since nitrogen is not reacting in this, now participating in the reaction, we can do a nitrogen material balance very quickly. We can say that the N2 is going to equal N3 N2. And you know that in this case, we'll have 0.02 times 100, giving me 2 kilomoles per hour. And that's going to be N3.N2. And I'm doing that right away because I don't want to forget about the nitrogen because I know what will happen. We're going to solve for all of my knowns. We're going to solve for how much methanol and water we get, how much CO2 and H2 we get. We're going to get really excited about that. We're going to forget all about poor nitrogen. So I just want to take care of that right now before we forget about it. So we have now taken care of nitrogen, and we're going to resume with our external reaction table. Okay, and we know we've got CO2 reacting with 3 hydrogen to give me a methanol and a water. And we're going to start at T equals 0. And in T equals 0, we know, so if we take 0.28, we take 0.28 and we multiply it by 100, N2 CO2 is 28. And we do the same thing for hydrogen, and we're going to get 70 to start. So for CO2, we have 28. We've got for hydrogen 70 moles. We do not have any methanol, and we do not have any water to start. Now at T equals T, what we're going to do is we're just going to start with looking at, we're going to use a variable to represent how much CO2 and hydrogen is consumed and how much methanol and water is generated. And in this case, we're going to let Z equal moles CO2 consumed. And generally with any reaction, I would like to have my Z term I don't want to confound my Z term with a coefficient. So for example, if I said Z equals moles hydrogen consumed, the issue is that now all the other reagents would be a third of what my hydrogen is. Because if I consume 30 moles of hydrogen, that really means I consumed 10 of CO2 and I made 10 of methanol and 10 of water. And therefore, everything else is 1/3 Z. So whenever possible, just make your Z coefficient, just keep your Z coefficient 1 and then scale anything up. So for example, with hydrogen, we're just going to have 3Z. And if there's a 2 or some other coefficient in front of a variable, you just make it that number times Z. So for example, with CO2, we're going to have 28 minus Z. With hydrogen, 70 minus 3Z. With Methanol, it's Z. Water, it's Z. Notice it's a 1:3 ratio. So, and I'm just going back to this example once again. If you had made hydrogen, the most hydrogen consumed Z, then what ends up happening is that this, the coefficient in front of the Z, then would have become 1/3 Z. See, it's 1/3, 1. The ratio is still the same, but it makes things a little bit more confusing if you try to do that, which is why I always like having at least a coefficient of 1 in front of the Z and then have everything else not be less than 1. All right. Thank you for humoring me with my side tangent. We're going to continue now on this adventure in solving for our unknowns. So now we've set up our extent of reaction table, so we know we're going to have all these amounts at time t equals t. So now what we can do is we can use my process specification. We've got a process spec that F conversion H2 equals 0.60. So that means that 60% of the hydrogen is consumed. 60% H2 consumed. So if we're rewriting this, we can say that F conversion is equal to N consumed over N naught. And there's two ways of going about it. You can either say this, you can say it's going to be N naught minus N final over N naught, or you can recognize with your extent of reaction what N consumed is going to be. And N consumed is going to be this subtracted term. So some of the times it could be Z, some of the times it could be 3Z. It really depends on what your coefficients are and what you're using, what you're saying is Z. And so for us, we can, since we've identified that this is my consumption term, we could also rewrite it as 3Z over N naught. And in that case, what we can do then is we can do some rearranging. So if it's F conversion equals all of this, we can then make it 3Z equals N naught. Let's fix that naught real quick. As soon as my eraser wants to work. There we go. N naught times F conversion. And now we can get that Z is going to equal N naught F conversion all over 3. And so now we substitute what we know. We've got 70 times 0.6 all over 3. And now what you should see, once you multiply all of that out, is that we're going to get a Z of 14. Now that we've calculated Z and we've seen that it's 14, what we can do is we can go back to our extent of reaction table and we can now calculate each of our flow rates in the exit stream. So for example, with carbon dioxide, we're going to get 28 minus 14, giving me 14. For hydrogen, 70 minus 3 times 14, and you'll get 28. And for methanol, you'll get 14, and water, you get 14. And now, if you sum all that up, we're going to get that N3 is equal to 28 plus 14 plus 14 plus 14 plus 2. And where did that 2 come from? As a quick reminder from earlier, you'll see that we figured out that 2 is the nitrogen. And therefore, stream 3 is going to be 72 kilomoles per hour. And now that we figured out our stream 3, what we're going to do is we're going to move on to our condenser. And the reason why is because if you look carefully at our condenser, what you're going to see is that we have a perfect separation where all the methanol and the water are coming out in the bottom stream, and the CO2, H2, and N2 are coming out in the distillate stream. And for that reason, we're going to go to the condenser because it's a very simple material balance separation. So if we draw out our condenser, stream 3, stream 4, stream 5, right? We've got all the methanol coming out, same deal with the water. And for stream 5, we've got CO2, H2, and N2. And we've got all those components in stream 3. And H2O. So if we, for example, did a material balance for methanol, CH3OH, what you'll see is that N3 CH3OH is going to equal N4 CH3OH. And as a reminder, for all our material balances, we're just doing for something like this, it's going to become in equals out because there's no reaction. So now that we've determined the methanol material balance, the water material balance will be the same, and it's going to end up being the same thing for CO2, H2, and N2. The only difference is that we're speaking with respect to stream 5 rather than stream 4. And for that reason, what you'll find out is that the methanol flow rate is going to be 14 kilomoles per hour. For water, it's going to be, again, 14 kilomoles per hour. And I'm just going to point out over here that our N4 dot then becomes 28 kilomoles per hour. And now for stream 5, we've got CO2 equaling N3 CO2, which is 14 kilomoles per hour. And then N5 H2, same deal, equals N3 H2, which equals 28 kilomoles per hour. And finally, we've got N5 N2 equaling N3 N2 equals 2 kilomoles per hour. And just like stream 4, I'm going to just tabulate all of that to get my N5 dot, which is going to be 44 kilomoles per hour. From here, what we're going to do is we'll move forward towards the splitter, and I'm going to redraw it over here. So we've got stream 5, we've got our splitter, and we've got stream 6 and stream 7. So we got CO2, H2, N2, and same thing in this stream, in stream 6, and in stream 7, where we've got CO2, H2, and N2. And the interesting thing about the splitter is that since it is splitting, there is nothing that's going on to change the composition within streams 5, 6, and 7. And for that reason, if we know the composition of one of our streams, we know the composition for all of the streams. And since we know everything about stream 5, we can do that. We can figure out what Y5 CO2, Y5 N2, and Y5 H2. And since it's going to, so for example, Y5 CO2, we're going to write it as N5 CO2 divided by N5 dot. And you'll get 14 divided by 42, divided by 44, right? Can't forget about that nitrogen. And that's going to give me 0.318. From there, we get the nitrogen. That's going to be 2 over 44, which is equal to 0.046. I will say, For nitrogen, since we are rounding that one a little bit extra, some of our final values may be a little bit off from what the true answers are, but for now and for the sake of the video, we're going to say that this is going to be good enough. And for hydrogen, we've got 28 divided by 44, giving me a mole fraction of 0.636. And like I said before, since it's a splitter, the mole fraction of CO2 in stream 5 is going to equal the mole fraction of CO2 in stream 6 and the mole fraction of CO2 in stream 7. Same thing for nitrogen. It's going to be the same mole fraction in both streams 6 and 7. And for hydrogen, sorry, that should be an H right there. There we go. H2. Okay. Now, looking at your splitter, we now know all our Y's in every single stream. We've got flow rates in stream 5, so we've got our M5 dot. The only issue is that I don't know anything else about stream 6 and 7. And for that reason, I can't really move any further with this problem, or rather with this unit, because I don't know anything else. So from here, what we'll have to do is we'll move forward to the mixing unit. And with the mixing unit, since that's the final unit, we'll have to work there to figure out the rest of my unknowns. So with the mixer, we've got stream 7, we've got stream 1, and I've got stream 2. Now, like the other time, like everything else we've seen right now, we've got a lot of CO2, N2, and H2 in these different streams. And from here, we also have a couple of known pieces of information. I know all my Y7s. So we've got Y7 CO2 equal to 0.318. Same deal with H2, 0.636. And Y7 N2 equals 0.046. For stream 1, I know my N2, Y1 N2 equals 0.005. And for stream 2, I've got all my Y's and I got my N2 dot. We know N2 is 100, and we've got Y2 CO2 equals 0.28. Y2 N2 is equal to 0.02. And Y2 H2 equals 0.70. And now we've got everything. We've got all our knowns listed out for my mixer. And from here, what we can do is look at our material balances around the mixer and try to identify a couple of them that can help me out with solving for the last bits of my unknowns. And in this case, we're just going to say the last bits are my N1 dot and my N7 dot. And once we figure out N7, obviously, we will go for N6 dot. So, as I said before, we're going to look at our material balances. And we'll start with our total material balance, which we know is N1 dot plus N7 dot equals N2 dot. And for us, we know what N2 dot is. We know it's 100. And from there, with our material balances, what we probably want to do is look for the next material balance that has the most information. And you'll see, for example, with CO2 and hydrogen, you have compositions in both in streams 2 and 7, which is great. However, nitrogen's got a little bit more information. We know everything in stream 2, 7, and stream 1. And for that reason, that's going to be really helpful for us, because when we write out the nitrogen material balance, we're going to see that we're going to have Y1 N2 multiplied by N1 dot plus Y7 N2 times N7 dot equals, I apologize, it's going to equal Y2 N2 N2 dot, which in this case, we can substitute in what we know. So we've got 0.005 N1 dot plus 0.046 N7 dot equals 0.02 times 100. So we know we've at least got the two. And looking at these two equations, what you'll see is that I've got N1 and N7 as my unknowns, and I've got it in both of these equations. And what I've now set up is a very small systems of equations where I've got two equations and I've got two unknowns, so I can rearrange and I can solve this algebraically or with the matrix to find my N1 and N7. And so for us, what I'll do is I'm going to take this equation and I'm just going to rewrite it as N1 dot equals 100 minus N7 dot. So I've now defined N1 in terms of N7. And from there, what I'll do is I'll take our nitrogen material balance and I'm going to substitute in my N1 dot. So it's going to be 0.005 times 100 minus N7 dot plus 0.046 N7 dot equals 2. And from here, we're going to get 0.5 minus 0.005 N7 dot plus 0.046 N7 dot equals 2. From here, what we'll do is we're going to combine my N7 terms and we'll combine my regular terms that have no variables. And what we'll get is 0.041 N7 dot equals 1.5. So from here, we will get N7 dot equals 1.5 divided by 0.041, which you will, if you do this calculation out, we're going to end up with 36.6 kilomoles per hour for my N7 dot. And now I can go back to my original equation, or not my original equation, but we'll go back to that other equation and we'll substitute in that N7 dot to get my N1 dot. So 100 minus 36.6 to give me 63.4 for N1 dot. And so now I have both N1 and N7, and we can go back to our splitter to determine N6 dot. So now back at the splitter, what we'll do, we will say that we know that we can do a total material balance. So we know N5 dot equals N6 dot plus N7 dot. We know N5, we know N7. So we can rearrange and we'll say that N6 dot is equal to N5 dot minus N7 dot. And that's going to equal 44 minus 36.6, which is going to give me 7.4 kilomoles per hour for N6 dot. All right, and now we have gotten all of our flow rates. And if you were so inclined and very curious about it, you can solve for your other Y's, Y1 CO2 and Y1 H2. But for the sake of this problem, I think we've got just about everything covered. And from here, the final step that we need is to perform a scale up. And the reason why is because, as you may remember from a lot earlier, we sacrificed a piece of information. We assumed a basis, right? Over here, we assumed a basis. And because we assumed that basis, we need to now return to get my true value for CH3OH in stream 4. So we're now going to go on down, get some fresh space, and we're going to scale up. And our scale up is equal to desired rate over actual rate. And so for us, our desired flow rate is 155 kilomoles per hour. And if you recall, and you can look through your notes, you'll see that the flow rate for methanol, when we assume the basis, was 14 kilomoles per hour. And so for this, we're going to get a scale-up factor of 11.07. If you want to be a little closer to what the true correct value is, you can give yourself a few more decimals. But again, for the sake of this video and working the problem out, this will be sufficient. And so from here, what we're going to do is we're going to take our N1 dot, for example, for N1, we'll take our N1 dot and I'll just put a little thing here. Our true N1 dot is going to equal scale up multiplied by N1 dot. And in this case, it's going to be 11.07 multiplied by 63.4 to give me 701.8 kilomoles per hour. So that's my true N1 dot. True/desired. And from here, you're just going to repeat this procedure for every single one of your flow rates. So by the conclusion, what you should get for all your flow rates are, for N2 dot, you'll get 1107. For N3 dot, it'll become 797. For N4 dot, it equals 310. For N5 dot, you'll get 487.1. And 6 dot is going to equal 84.1. And N7 dot is going to equal 405.2. And again, these are all going to have kilomoles per hour as our units. And there it is. You have solved a multi-unit process with a reaction. So thanks a lot for tuning in, and I'll see you in the next one.